Training in Weld Quality Assurance and Quality Control. Section number 4, Discontinuities and Defects. Topic number 2, the identification and definition of weld discontinuities and defects. The objective of this topic is to be able to identify and define the various types of discontinuities and defects. In order to successfully evaluate weldments, the weld inspector should have the ability to identify weld discontinuities. To simplify identification, they can be grouped into 3 classes, each having different characteristics. The first group of discontinuities relates to shape, size, and contour, that is, the external dimensions of a weld. The second group relates to the internal consistency of welds and is often referred to as structural discontinuities. And the third group, weld and base metal properties, relates to the match between weld metal and base metal. All affect the ability of a weld to perform based on service requirements. The first group to be considered is the type of discontinuity related to shape, size, and contour. This group can be further broken down to welds that show excessive reinforcement, incorrect size, incorrect profile, and incorrect final weldment dimensions. Excessive face reinforcement is defined as extra metal deposited in a weld, forming a highly convex contour on the side of the joint from which welding is done. Excessive root reinforcement is extra weld metal deposited in the root of the weld. This is generally more common with joint designs which have root openings. In addition to excessive reinforcement, welds may be unacceptable if they are incorrect in size. The size of a groove weld is measured by the depth of the effective throat, the shortest distance from the root of a weld to its face, minus any reinforcement. Generally, it is equal to the base metal thickness on full penetration welds. When the plates are of unequal thickness, then the thickness of the thinner plate determines the size of the groove weld. A slight reinforcement is usually specified to ensure adequate joint penetration. It is sometimes believed that a high amount of reinforcement serves to increase the strength of the welded joint. This is not true. Not only is excessive reinforcement wasteful, but it also decreases the working strength of the joint due to concentration of stresses at the toes. The size of a fillet weld is often designated as its shortest leg length, a measurable dimension used to deposit the weld. The leg is the distance from the root of the joint to the toe. For strength, the size of a fillet weld is the leg length of the largest isosceles right triangle that can be inscribed within the weld. For flat and convex welds, the leg size is equal to the effective size for strength. However, for concave welds, the effective size for strength is less than the actual leg length. Welds that do not meet the minimum size standard can be cause for unacceptability. Welds of incorrect size may be determined visually with the use of weld gauges or by comparison with approved workmanship samples. Incorrect weld profile is a common problem and is best described as a weld that does not meet the requirements for size or contour. An example of this is overlap, which is the bulging or protruding portion of a weld that extends beyond the toe, face, or root. This type of discontinuity in both fillet and groove welds can reduce the size and strength. In both cases, stresses are concentrated at the weld toes, causing weak points that may fail. Another discontinuity related to weld profile is insufficient throat or underfill. This occurs when a weld face or root is depressed or extends below the adjacent base metal surfaces, resulting in a throat less than specified by the designer. A type of weld problem also related to weld profile discontinuities is undercut. This is best defined as a groove melted into the base metal adjacent to the toe or root of a weld and left unfilled. Undercut is most commonly found at the sidewall or face of a groove, at the edge of a weld or layer. It is also commonly present at the toe of the last or cover pass of a welded joint, resulting in a reduction of base metal thickness at the point of undercut. In fillet welds, undercut tends to reduce the size and strength of the weld, as well as promoting stress concentrations at the toes. Another profile-related discontinuity is excessive convexity, which is a highly convex contour formed by excessive reinforcement. Discontinuities can be related to incorrect final weldment dimensions, such as those caused by distortion and warpage. The non-uniform expansion and contraction of weld and base metal during the heating and cooling process contributes to weldment distortion and warpage. If warpage has changed the required dimensions of the total weldment, the actual weld itself may be acceptable, but the weldment isn't. The second group of discontinuities to be discussed are those related to internal inconsistencies or irregularities, commonly referred to as a structural type defect. These include discontinuities such as cracks, porosity, slag inclusions, tungsten inclusions, incomplete fusion, and inadequate joint penetration, all of which can have a considerable effect on the quality of a weld and which must be analyzed to determine their acceptance or rejection. Cracks are defined as a fracture that displaces an opening or a split in the weld or base metal. There are a variety of types, all of which can be devastating to the strength of the weld. Cracks can be classified into two types, either hot or cold. Hot cracks occur at high temperatures during solidification of the weld puddle, usually above 400 degrees Fahrenheit on steels. Cold cracks occur after solidification is complete. Both hot and cold cracks can be further categorized by physical relationships, that is, their location within the weld or weldment. For example, a longitudinal crack runs along parallel to the axis of the weld. The transverse crack runs just the opposite of the longitudinal crack, perpendicular to the axis of the weld, and is often located near or in poor restarts or other internal discontinuities. Crater cracks occur in the depression left at the termination of the weld bead. Although they are fairly small, they can be very serious defects. With this type of defect, cracking may occur at the point of stress concentration when the weldment is subjected to a high load. For this reason, crater cracks are especially serious when located near the end of a weld seam, since they can lead to transverse or longitudinal cracks that will cause the weld to fail. Crater cracks can appear in the shape of a star or in a single direction, either longitudinal or transverse. Throat cracks are longitudinal in the throat of the weld and originate from the face or root. Toe cracks usually occur during cooling and originate and grow from the toe of the weld, where high amounts of stress are most common. Root cracks are located along the root of the weld. They can occur during or after solidification of the weld puddle. An arc strike is a heat-affected surface, a localized, remelted metal surface, or change in surface profile caused by an arc. Arc strikes are too often considered just a blemish, but in fact they can be serious defects that can lead to cracking of the weld or weldment if not removed by sufficient grinding. Heat-affected zone cracks, also called underbead cracks, generally occur during the cooling cycle after solidification of the weld and normally do not extend to the surface of the weldment. They are usually short in nature, but can connect with others to become continuous cracks. Heat-affected zone cracks can also occur after the part is placed in service because of embrittlement of the weld and the heat-affected zone. The next type of discontinuity is porosity, which is best described as gas entrapment cavities formed during solidification of the weld. They can appear in various forms, scattered uniformly throughout the weld, or grouped into clusters at specific points. Linear porosity generally follows a line parallel to the axis of the weld. Piping porosity, also called wormholes or blowholes, appear as a cylindrical cavity, often with some slag entrapment. Porosity can appear at the surface of a weld, or it can be located internally. A discontinuity similar to porosity are slag inclusions, which are non-metallic solid materials trapped within the weld metal or between the weld and base metal during solidification. Internal slag entrapment is often elongated and generally parallel with the weld axis and occurs between passes or next to the face of a groove weld. This type of inclusion is sometimes called wagon tracks and is commonly found in pipe welds. Another form of entrapment discontinuity is the metallic or tungsten inclusion. These are electrode particles trapped in the weld deposit and come from the electrodes used in gas tungsten arc or plasma arc welding. Tungsten can appear in a weld one of two ways, either scattered in fine particles or in one large particle, as in the case when the electrode tip is broken off in the puddle. Yet another type of internal weld discontinuity is incomplete fusion, which is the failure of the liquid weld metal to flow into and fuse the total face area of the joint. A discontinuity with similar causes is inadequate joint penetration, which is defined as penetration which is less than specified. This type of defect is located at the root of the weld. The final class of discontinuities to be discussed is related to weld and base metal mechanical and chemical properties. In some cases, specific mechanical, chemical, or physical properties are required in welds. The requirements depend upon the type of material being welded and the service requirements of the weldment. Mechanical properties that must be checked against prescribed requirements include tensile strength, yield strength, ductility, and impact strength. Tensile strength is the resistance to breaking offered by metals when subjected to a pulling stress. Yield strength is the maximum load per unit area that a material can stand without being permanently deformed. Ductility is the ability of metals to be drawn, stretched, or twisted without breaking. And impact strength is the ability of a material to resist sudden or shock loading. Chemical properties must also be checked against prescribed requirements to avoid incorrect weld metal composition. The base and weld metal must be chemically compatible, but other chemical elements in the environment surrounding the welding process must also be considered. For example, nitrogen, hydrogen, and oxygen cannot be avoided if ordinary air comes in contact with the weld. Fluxes and shielding gases must also be compatible. Any incorrect match of mechanical or chemical properties between the weld and base metal may lead to weld failure, For example, joining stainless steel pieces with a carbon steel filler metal. In this case, the weld would not possess the same corrosion-resistant properties as the base metal. Base metal property requirements may be defined by applicable specifications or codes. Departure from these requirements may be considered cause for rejection. Other conditions of the base metal which may impair the ability of a material to perform as expected can include laminations, delaminations, seams, laps, and lamellar tears. Laminations are generally a flat, elongated sandwich discontinuity normally found near the center of structural metals and are caused during production at the mill. They generally run parallel to the manufactured surface of the plate. Metals containing laminations cannot reliably carry stresses in the through thickness direction and are therefore prone to failure. Laminations that have separated due to stresses are known as delaminations. Seams and laps are longitudinal base metal discontinuities and are the most critical when located perpendicular to the principal stress, since they often propagate as cracks. Welding over seams and laps will only cause further cracking to occur. Cracking is less likely to occur when the stress is located parallel to the seam or lap. Lamellar tears are discontinuities that occur during or after welding and usually appear as a stair-step defect caused by contraction forces during solidification. Lamellar tears may extend over long distances and are located deeper than heat-affected zone cracks, which differ in shape, cause, and location. Welders and welding operators often ask the following questions about weld defects. Which discontinuities contribute to weld failure? Which ones may pass inspection? And are there jobs on which weld discontinuities are permitted? To answer these questions, the weld inspector should have a working knowledge of the service requirements of the weldment, as well as the codes and standards that apply to any particular job. In general, the inspector's goal should be to ensure the closest possible accuracy to the details of the weldment specifications. As the work becomes more critical, the attention to detail becomes more vital, and very tight tolerances are required in critical or code work because of the necessity for high strength in load conditions of heat, pressure, or stress. Welding inspectors must be aware that welders who consider themselves craftsmen always strive to produce sound welds with good appearance.